Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let us see the beam one time. In this beam, there are three spans: span AB, span BC and span CD. In the span AB, we are having point load 24 kN acting on the center. In the span BC, we are having UDL 12 kN per meter acting for the full span. In the span CD, we are having a point load 25 kN acting at 3 meter from the point C. In the point A, there is a fixed support. In the point B, in the point C, and the point D, we are having hinged supports. The moment of inertia for the span AB is 2I, for the span BC it is 1.5I, and for the span CD it is 2I. Length of the span AB is 4 meter, length of the span BC is 3 meter, and length of the span CD is 5 meter. In this beam there are 5 moments. In the fixed support there will be a moment, that is MAB. In the joints there will be 2 moments. In the joint B we are having MBA and MBC. In the joint C we are having MCB and MCD. Point D is a simply supported end. In the simply supported end there will be no movement, so MDC is equal to 0. So in this analysis we have to find 5 movements. Also we have to find 4 reactions: RA, RB, RC and RD. Now let us calculate the fixed end moments. For calculating fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now, let's see the formulas to calculate the fixed end moments. Here you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load acting on the center, so we have to select this condition. The formulas are minus WL upon 8 and positive WL upon 8. In the span BC, there is UDL acting for the full span, so we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. In the span CD, there is a point load. That point load is not acting on the center, so we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. Now let's apply these formulas and find out the fixed end moments. In the span AB, there is a point load acting on the center. We have already seen the fixed end moment formulas: minus WL upon 8 and positive WL upon 8. M of AB is negative because it is acting in the anticlockwise direction. M of BA is positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 24, L is 4. When we apply the values inside the formulas, we are getting M of AB is equal to minus 12 kN meter and M of BA is equal to 12 kN meter. In the span BC, UDL is acting for the full span. We have already seen the fixed end moment formulas: minus WL square upon 12 and positive WL square upon 12. Let us apply the values inside the formulas. W is 12, L is 3. After applying all of the values inside the formulas, we are getting M of BC is equal to minus 9 kN meter and M of CB is equal to 9 kN meter. Now let us calculate the fixed end moments in the span CD. In the span CD, we are having a point load. This point load is not acting on the center. We have already seen the formulas for the fixed end moments minus WAB square upon L square and positive WA square B upon L square. Let us apply the values inside the formulas. W is 25, A is 3, B is 2, L is 5. After applying the values inside the formulas, we are getting M of CD is equal to minus 12 kilonewton meter and M of DC is equal to 18 kilonewton meter. In the moment distribution method, we have to find the distribution factor. We have to find the distribution factor only in the joints because in the ends we can easily say the distribution factor. In the fixed ends, the distribution factor will be 0, and in the roller supported and hinged ends, the distribution factor will be 1. In the point A, we are having fixed support, so the distribution factor for AB will be 0. In the point D, we are having hinged support, so the distribution factor for DC will be 1. In this case, we have to calculate the distribution factor only in the joints B and C. For calculating the distribution factor, we need to find the stiffness. Let us see the formulas to calculate the stiffness at the joints. If the ferrand is fixed, the formula is 4EI upon L. If the ferrand is hinged or with roller support, the formula is 3EI upon L. If the ferrand is continuous, the formula is 4EI upon L. Now let us apply these formulas in this beam and find out the stiffness values. First, let us calculate the stiffness from the joint B. From the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the point B, we have to look at the point A. In the point A, we are having a fixed support. If the ferrand is fixed, the formula is 4EI upon L. Here, the moment of inertia is 2I. So, instead of I, we have to apply 2I. Length is 4 meter. Finally, we are getting 2EI. Now, let us calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous because after the point C, we are having a span CD. If the ferrand is continuous, the formula is 4EI upon L. Here, moment of inertia is 1.5I and length is 3 meter. After applying inside the formula, we are getting 2EI. Now, let us calculate the stiffness values from the joint C. From the joint C, we have to calculate the stiffness for CB and for CD. First, let us calculate for CB. For that, from the joint C, we have to look at the point B. The point B is continuous because after the point B, we are having a span AB. If the ferrand is continuous, the formula for stiffness is 4EI upon L. Here, moment of inertia is 1.5I and length is 3 meter. After applying in the formula, we are getting 2EI. Now, let us calculate for CD. For that, from the point C, we have to look at the point D. In the point D, we are having a hinged support. If the ferrand is hinged, the formula is 3EI upon L. Here, the moment of inertia is 2I and length is 5 meter. After applying both of the values inside the formula, we are getting 1.2 EI. Now let us calculate the summation of stiffness. In the joint B, there are two stiffness values. Let us add them. After adding, we are getting 4EI. In the joint C also, there are two stiffness values. Let us add them. After adding, we are getting 3.2 EI. Now let us calculate the distribution factor. The formula for distribution factor is K by summation of K. We have already calculated K and summation of K. For BA, K is 2EI, summation of K is 4EI. When we apply inside the formula, we are getting 0.5. For BC, K is 2EI, summation of K is 4EI. When we apply inside the formula, we are getting 0.5. In the same way, we can calculate the distribution factors in the joint C. Now, let us start making the moment distribution table. In the table, first let us enter all of the members. Then let us enter the distribution factor values. For AB, the distribution factor is 0 because in the point A, we are having fixed end. For DC, the distribution factor is 1 because in the point D, we are having hinged supported end. In the joints B and C, we have calculated the distribution factors. Let us enter them. Then let us enter the fixed end moment values. In the point D, there will be no moment because it is a simply supported end. So MDC is equal to 0. In the table, we have to make DC 0. For DC, the fixed end moment is 18. When we add minus 18 with this 18, it will be 0. So we have released DC and we have to give the carryover from DC to CD. So half of minus 18 from DC will go to CD. We know that minus 18 upon 2 is equal to minus 9. Let us enter that. Now let us calculate the adjusted fixed end moments. For AB, BA, BC and CB, there are no changes. For CD, we have to add these two values. After adding, we are getting minus 21. Now let us make the first distribution. The distribution can be done only on the joints. In this problem, we are having two joints, joint B and joint C. First, let us make the distribution in the joint B. Under the joint B, we are having the members BA and BC. For them, we are having the fixed end moments. For making the distribution, we have to add these two fixed end moments and multiply with the distribution factors. First, let us do for BA. For that, we have to add these two values and multiply with the distribution factor at BA. When we do that, we are getting positive value. Since we got a positive value, we have to enter inside the table as negative. Now let us do for BC. For that, we have to add these two values and multiply with the distribution factor at BC. Here also we are getting a positive value, so we are entering as negative. Here both of the values are same. Since we are having the same distribution factors for BA and BC, now let us make the distribution in the joint C. First, let us do for CB. For that, we have to add these two values and multiply with the distribution factor at CB. When we do that, we are getting a negative value. So, we are entering inside the table as positive. Now, let us do for CD. For that, we have to add these two values and multiply with the distribution factor at CD. Here also, we are getting a negative value. So, we are entering inside the table as positive. Now let us make the carryover. We cannot make the carryover between CD and DC because we have already released DC and made it as 0. The carryover only can be done between AB and BA and between BC and CB. First, let us do the carryover between AB and BA. For AB, there is no distribution, so we cannot make the carryover. From BA, half of minus 1.5 will go to AB. Minus 1.5 upon 2, we will get minus 0.75. Now let us make the carryover between BC and CB. Minus 1.5 upon 2, we will get minus 0.75, and 7.5 upon 2, we will get 3.75. Now let us make the second distribution. First, let us do in the joint B. For BA, there is no carryover. For BC only, there is carryover. So, under BA and BC, there is only one value. For making the distribution, we have to multiply this value with the distribution factors. First, let us do for BA. For that, we have to multiply 3.75 with the distribution factor at BA. When we do that, we are getting positive value. Since we are getting positive value, we have to enter inside the table as negative. Now, let us do for BC. For that, we have to multiply 3.75 with the distribution factor at BC. Here also we are getting a positive value, so we are entering inside the table as negative. Now let us make the distribution in the joint C. For CB there is carryover. For CD there is no carryover. So here also we are having only one value. First let us make the distribution for CB. For that we have to multiply minus 0.75 with the distribution factor at CB. When we do that, we are getting a negative value, so we are entering inside the table as positive. Now let us do for CD. For that, we have to multiply minus 0.75 with the distribution factor at CD. Here also we are getting a negative value, so we are entering inside the table as positive. Now let us make the carryover. First, let us do between AB and BA. Half of minus 1.875, we will get minus 0.938. Now let us make the carryover between BC and CB. Minus 1.875 upon 2, we will get minus 0.938. 0.469 upon 2, we will get 0.235. In this way, we can make more distributions and carryovers. We can stop the process when we are getting very small values. I have done up to the sixth distribution. I have stopped in the sixth distribution because I am getting very small values. In the final distribution, we don't have to make the carryover for all the values. Only we have to give the carryover to the fixed ends. In the point A, we are having a fixed support. So we have to give the carryover from BA to AB. Minus 0.012 upon 2, we will get minus 0.006. Now let us add all of the values and find the final moments. We have to add the values from the adjusted fixed end moments. After adding all of the values, we are getting the final moments. For MAB, we are getting a negative value. That means MAB is acting in the anticlockwise direction. For MBA, we are getting a positive value. That means it is acting in the clockwise direction. For MBC, we are getting a negative value. That means it is acting in the anticlockwise direction. For MCB, we are getting a positive value. That means it is acting in the clockwise direction. For MCD, we are getting a negative value. That means it is acting in the anticlockwise direction. Now let us calculate the vertical reactions. First, I am going to take the span AB and calculate the vertical reactions. In the span AB, there are two movements, MAB which is acting in the anticlockwise direction and MBA which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that I am going to take moment about B. In this case I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4, so 4 RA. The point load is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 2 meter, so minus 24 into 2. Then we are having two movements. This movement is acting in the anticlockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 13.37 kilonewton. Now we can easily calculate RB1 by applying the rule summation of vertical forces is equal to 0. In this span, we are having three loads, RA, RB1 and 24 kilonewton. RA and RB1 are acting upwards, so both are positive. 24 kilonewton is acting downwards, so it will be negative. We have already calculated RA, we can apply that. Finally, we are getting RB1 is equal to 10.63 kilonewton. Now, let us take the span BC and calculate the vertical reactions. In the span BC, there are two movements, MBC which is acting in the anticlockwise direction and MCB which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 3 meter, so 3 RB2. The UDL is acting towards the point C in the anticlockwise direction, so it will be negative. For the UDL, we have to multiply with the distance and distance by 2. Here the distance is 3 meter, so 3 into 3 by 2. Then we are having two movements. 8.34 is acting in the anticlockwise direction, so it will be negative. 15.81 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2, which is equal to 15.51 kilonewton. Now, using the rule, we can calculate RC1. RB2 and RC1 are acting upwards, so they will be positive. UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. So 12 into 3, we have already calculated RB2. Let us apply that here. Finally, we are getting RC1 is equal to 20.49 kilonewton. Now let us take the span CD and calculate the vertical reactions. In the span CD, there is only one movement, MCD, which is acting in the anticlockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. RC2 is acting towards the point D in the clockwise direction, so it will be positive, and the distance is 5 meter, so 5 RC2. The point load 25 kilonewton is acting towards the point D in the anticlockwise direction, so it will be negative and the distance is 2 meter, so minus 25 into 2. This movement is acting in the anticlockwise direction, so it will be negative. Finally, we are getting RC2, which is equal to 13.16 kilonewton. Using the rule summation of vertical forces is equal to 0, we can calculate RD. After calculations, we are getting RD, which is equal to 11.84 kilonewton. In the point B and in the point C, we have calculated the reactions 2 times. For RB, we have to add RB1 and RB2. Finally, we are getting RB. For RC, we have to add RC1 and RC2. After adding, we are getting RC. Now, we are going to draw the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am going to calculate the values from the point A towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. Using the concept, I have made the calculations. After making the calculations, we can draw the shear force diagram. Now, we are going to draw the bending moment diagram. Before drawing the bending moment diagram, we have to make the free moment diagram and the end moment diagram. Then we can combine both of them to form the bending moment diagram. For making the free moment diagram, we have to consider every span as a separate simply supported beam. First, let us take the span AB. If in the simply supported beam, point load is acting on the center, the formula to calculate the maximum bending moment is WL upon 4. Here W is 24, L is 4. When we apply in the formula, we are getting 24 kilonewton meter. If in the simply supported beam, UDL is acting for the full span, the formula to calculate the maximum bending moment is WL square upon 8. Here W is 12, L is 3. When we apply in the formula, we are getting 13.5 kilonewton meter. In the span CD, we are having a point load. This point load is not acting on the center. The formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 3, B is 2, L is 5. When we apply all of the values in the formula, we are getting 30 kilonewton meter. For the point loads, the diagram will be in the shape of a triangle. For the UDL, the diagram will be in the shape of a parabola. Now let us make the end moment diagram. Using the end moments, we have to make the end moment diagram. To mark these values above the line or below the line, we have to see the direction of the curves. All the curves are indicating upwards. That means all the points in the end moment diagram will be coming above this line. In the point B, we are having two moments. In the point C also, we are having two moments. Even though we are having two moments, we have to make only one point because both of these arrows are indicating upwards. In the point C also, both of these arrows are indicating upwards. If the end moment diagram comes above the line, it will be negative. If it comes below this line, it will be positive. Now let us combine the free movement diagram and end movement diagram. Wherever they are acting alone, without mingling with each other, we have to mark the values with the sign. Here end movement diagram is acting alone. Here free movement diagram. Here end movement diagram. Free movement diagram, end movement diagram, and free movement diagram. Wherever they are acting together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.